Good morning. I'm Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today I'm going to deliver a lecture on chemistry, whose subject code is KAS 102T. The course comprises of 5 modules, namely atomic and molecular structure, spectroscopic techniques and applications, electrochemistry, water analysis, and polymer. These are the reference books from where I have taken my material. They are University Chemistry by B.H. Mahan, University Chemistry by C.N.R. Rao, Organic Chemistry by I.L. Finar, Physical Chemistry by Glaston, Engineering Chemistry by S.S. Dara, Polymer Chemistry by Bilmer, and Engineering Chemistry by Satya Prakash. Now coming to Module 1. The Module 1 comprises of molecular orbital theory for diatomic molecules, band theory of solids, liquid crystal and its applications, point defects in solids, structure and applications of graphite and fullerenes, concept of nanomaterial and its applications. Now coming to the first topic, that is Introduction to Molecular Orbital Theory. Then the molecular orbital theory and its application to form homo and heterodiatomic molecules. Before I start with MOT, that is molecular orbital theory, I'll give a brief account of the valence bond theory, that is VBT. Now, the VBT says that the molecule is made up of atoms. Electrons in atoms, they occupy atomic orbitals. Now, these atomic orbitals, they may or may not be hybridized. Hybridization is a concept where intermixing of slightly different energy orbitals is there to give the orbitals of degenerate energy. If hybridized atomic orbitals combine to produce hybrid orbitals, which can overlap more effectively with orbitals of other atoms, therefore stronger bonds are formed. Then these overlapping orbitals, they must have unpaired electrons with antiparallel spins or the opposite spins. Bonds are formed because of the electrostatic attraction between anti-spin electrons and nuclei, because the electrons, they have the negative charge and the nuclei has the positive charge. Extent of overlapping, it depends upon the nature of the orbitals and the type of overlapping. Nature of the orbitals, whether it is the s orbital or the p orbital, and type of overlapping, whether a sigma bond is going to be formed or a pi bond is going to be formed. That is the head-on overlapping or the lateral overlapping will take place. The next point is atomic orbitals remain even after atoms are chemically bonded in a molecule. That means the atomic orbitals, they retain their identity even though the atoms have been converted into a molecule. The concept of resonance is applicable to VBT. VBT could explain the structure of a number of compounds, but there are certain drawbacks related to it. First, the VBT could not explain the stability of 1 and 3 electron bonds having unpaired electrons. Next, it could not explain the magnetic behavior of oxygen. According to VBT, oxygen is diamagnetic in nature. Next, it could not explain the color and magnetic behavior of compound. Why certain compound they show color and why the compound they show different magnetic behavior when kept in the magnetic field. Now, coming to molecular orbital theory, it was developed by Hund and Mulliken in 1932. Now, this theory states that the valence electrons, they are associated with all the nuclei in a molecule. That is, the valence electrons of any atom, they are not the electrons of the atom when they bind in a molecule. They are the electrons of the molecule. Atomic orbitals of different atoms, they must combine to produce molecular orbitals. Electrons are considered as particle or wave. Electrons are polycentric, therefore electrons in a molecule, they occupy molecular orbitals. And the wave function showing the molecular orbitals, it may be obtained by linear combination of atomic orbitals, that is the LCAO. The concept of resonance, it is not applicable to MOT. The combining atoms or the combining orbitals, they must be of same energy and same orientation for the maximum overlapping. The two atomic orbitals combining to form the molecular orbitals, they give rise to a bonding molecular orbital and an anti-bonding molecular orbital. That is, number of molecular orbitals is equal to the number of atomic orbitals which are combining to form the molecular orbital. Now, the electrons which are present in the bonding molecular orbital, they provide stability to the molecule, whereas the electrons which are present in the anti-bonding molecular orbital, they provide instability. The number of atomic orbitals must be equal to the number of molecular orbitals formed. That means, number of atomic orbitals, if two atomic orbitals are combining, then they are going to result into two molecular orbital formation. The molecular orbitals, like atomic orbitals, they are filled in according to the Aufbau principle. The Aufbau principle states that the orbitals which are lower in energy, they are going to be filled first. Then they are filled according to the Pauli exclusion principle, which states that the two electrons in the same orbital cannot have the same set of 4 quantum numbers. At least their spin quantum number will be different. And the Hund's rule, which states that the pairing will not take place unless and until the same energy orbitals are singly occupied. So, these 3 rules are applicable to MOT. Coming to the central theme, at the quantum mechanical level, the molecule is viewed as a collection of nuclei surrounded by delocalized molecular orbitals. The atomic wave function is summed to obtain the molecular wave function. If wave functions, they reinforce each other, a bonding molecular orbital is formed. That means a region of high electron density exists between the two nuclei which are forming the bond. And if the wave functions, they cancel each other, then the antibonding molecular orbital is formed. That is, a node of 0 electron density occurs between the nuclei. Formation of molecular orbitals by linear combination of atomic orbitals. The atomic orbitals of these atoms may be represented by the wave function psi a and psi b. Suppose the two atomic orbitals which are combining to form the molecular orbital, they are shown by the wave function psi a and psi b. Now, the wave function for the molecular orbital is shown by either the addition of psi a with psi b or by the subtraction of psi a and psi b. That is, psi mo, which is being formed, it can be formed by either the additive combination of psi a with psi b. That is, the wave function of psi a and psi b are going to be same, or diagrammatically they can be shown. If this is the wave function for psi a, then this is the wave function for psi b. That is, they are of the same sign. As a result, this will be the wave function of psi AB, which is formed by the additive combination or constructive interference. The second case which may arise is when the wave function of psi A and psi B are different. If psi A is positive in nature, then psi B can be negative in nature. This results in the formation of destructive interference or subtractive combination. For example, if this is psi A, which is positive, and this is the wave function for psi B, when combination will take place, it will result in the formation of this is going to be the wave function for psi AB. That is, this is formed by the destructive combination of both the atomic orbitals. So, here two types of combinations are possible. As a result, two molecular orbitals, namely sigma and sigma star, are formed. If construction interference is going to take place, then sigma bond will result, and if destructive combination is going to take place, then sigma star molecular orbital will be formed. And here the coefficient C, they indicate the contribution of atomic orbitals to the molecular orbital. Now, here again it is being shown how constructive and destructive interference has taken place. Now, here are the two nuclei, atomic, and this is the distance between the two nuclei. When both are positive, these waves are going to reinforce each other, and hence the amplitudes of wave function is going to get added. So, the sigma bond will result with the addition of psi A and psi B. In the second case, this is the wave function of psi A, but psi B is negative in nature. As a result, on the combination of these two, the waves are going to cancel each other and a node is being formed at the center. Now, here the amplitudes of wave functions are getting subtracted, which are going to result in the formation of sigma star, which is nothing but wave function of psi A minus wave function of psi B. So, if two atomic orbitals are combining, two types of combination can take place. Either it can be additive combination or it can be subtractive combination. So, on combination of two atomic orbitals, two molecular orbitals will be formed, one by the additive combination which will result in the formation of bonding molecular orbital, and the another one on subtractive combination which will result in the formation of antibonding molecular orbital. Now, coming first to the molecular orbital of the hydrogen molecule. Now, this is the potential energy of the isolated hydrogen atoms. These are the two hydrogen atoms isolated, and when the two atoms they combine, then they are going to result in the formation of two molecular orbitals, one which is of lower in energy formed by the additive combination, that is the bonding molecular orbital, and the energy difference between energy of isolated hydrogen atoms and the bonding molecular orbital, it is known as the stabilization energy. So, first molecular orbital will be bonding, and the next, which is forming by the subtractive combination, that is the anti-bonding molecular orbital, that is sigma star 1s. So, when two atoms or two atomic orbitals are combining, two molecular orbitals are being formed, one lower in energy and another one higher in energy. So, bonding molecular orbital and the another one anti-bonding molecular orbital. Now, the considerations. Bond order. Bond order is given by number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding molecular orbital divided by 2. Higher is the bond order, stronger is going to be the bond formed between the two atoms. And if the bond order is 0, it indicates that the molecule does not exist. There is no bonding between the two atoms. And the molecular electron configurations, highest occupied molecular orbital, it is given by HOMO, and the lowest unoccupied molecular orbital, it is given by LUMO. Now, here an example is taken as H2, which is sigma 1s2. So, both the electrons get filled into the bonding molecular orbital. This is the again molecular hydrogen. Here these are the two isolated atomic orbitals of hydrogen atom. So, 1s and 1s of two hydrogen atoms, two atomic orbitals are combining, they are going to form the two molecular orbital, one lower in energy which is the sigma 1s, and another one which is higher in energy, which is the sigma star 1s. So, these two electrons, because each molecular orbital can accommodate at a maximum of 2 electrons with anti-parallel spins. So, both the electrons they get filled in the sigma 1s orbital, and sigma star 1s of hydrogen atom remains empty. So, the H2 bond order, which is calculated as number of electrons in the bonding, which is 2, minus number of electrons in the anti-bonding, which is empty, that is 0, divided by 2 is equal to 1, which means that between two hydrogen atoms there exists a single bond, or the two hydrogen atoms are joined together by a single bond. These are the various energies which are given. Now, predicting the stability of H2 plus and H2 minus, and also predicting whether these two molecules will show their existence or not. Now, H2 plus is formed, that means H2 molecule has 2 electrons. So, when it is going to result in the formation of H2 plus, there is going to be only 1 electron. One atomic orbital of hydrogen will remain empty. So, here atomic orbital of hydrogen has 1s1, 1 electron, while the other atomic orbital of hydrogen is empty, there is no electron. These are the two molecular orbitals which are being formed on the combination, and this 1 electron enters into the molecular orbital or the bonding molecular orbital, that is the sigma 1s. Now, here the bond order is being calculated as half 1 minus 0. There is 1 electron in the bonding, whereas the anti-bonding is empty. So, 1 minus 0 is equal to half, which shows that H plus molecule shows its existence, because the bond order of H2 plus is greater than 0. Similarly, predicting the stability of H2 minus, in this case out of the two, one atomic orbital will have one electron more in comparison to the hydrogen molecule. So, this molecule has 1s1 electron, whereas the another atom of hydrogen, it has 2 electrons. The first 2 electrons with anti-parallel spin, they enter into the bonding molecular orbital, that is the sigma, and the remaining 1 electron, it enters into the sigma star orbital, that is the anti-bonding molecular orbital. So, again when we calculate the bond order, bonding molecular orbital contains 2 electrons, whereas the anti-bonding molecular orbital contain only 1. So, bond order will be 2 minus 1 divided by 2, which is again half, which shows that H2 minus molecule also exists in nature. Next, coming to He2 plus molecule versus helium molecule. Now, electronic configuration of He is 1s2, it contains 2 electrons. So, in He2 plus, one of the atomic orbitals will have 1 electron less. Here, atomic orbital of helium atom 1s has 2 electrons, but in this case the 1s orbital of helium has only 1 electron, that is, it is the atomic orbital of He plus. Now, again the 2 electrons, they enter into the bonding molecular orbital, which results in the formation of sigma 1s, and the remaining 1 electron, it enters into the sigma star 1s, and the bond order again is calculated to be half. Now, coming to He2 molecule. In the case of He2 molecule, both the 1s has 2 electrons, out of which 1 and 1 electron, they enter into the sigma 1s, which is the bonding molecular orbital, and the remaining 2 enter into the anti-bonding molecular orbital, that is the sigma star 1s. Now, we calculate the bond order. The bond order will be given by 2 minus 2 divided by 2, which comes out to be 0. Now, here the bond order is 0, which indicates that the helium molecule does not show its existence. For any molecule to show its existence, its bond order should be greater than 0. Now, this is the table showing the bond length versus bond order. Bond order and bond length, they are inversely proportional to each other. So, higher is the bond order, lower is the bond length. Now, here H2 plus has 1 electron in the bonding, 0 electron in the anti-bonding, and the bond length is 1.06 and the bond strength is 269 kilojoules per mole. So, here it is again hydrogen molecule, because bond order has become greater, so bond length will decrease. H2 plus bond order was half, and here H2 the bond order is 1. So, when bond order increases, bond length decreases and bond strength increases, because bond strength is directly proportional to bond order. Now, coming to the next row, that is the 2s and the 2p orbitals. So, the next molecule, it is Li2, lithium molecule. The electronic configuration of lithium is 1s2, 2s1. So, there are 3 electrons in the atomic orbitals of lithium. So, this diagram depicts the lithium molecule. 1s of lithium has 2 electrons, these are the atomic orbitals. So, first 2 electrons enter into the sigma 1s, the next 2 enter into the sigma star 1s, and the 2s orbitals of lithium has only 1 electron each, and these 2 electrons enter into the sigma 2s orbital. On calculation of bond order is calculated as number of electrons in the bonding molecular orbital. So, here 2 plus 2, 4 electrons in the bonding molecular orbital minus 2 electrons in the antibonding molecular orbital divided by 2. So, the bond order comes out to be 1. Similarly, coming to beryllium molecule. In the case of beryllium molecule, again the electronic configuration of beryllium is 1s2, 2s2. So, both the atomic orbitals will have 4 electrons, 2 in 1s and 2 in 2s. So, 1s of both the beryllium has 2 electrons, 2 enter into the sigma 1s and next 2 enter into the sigma star 1s. Similarly, in the 2s orbital of beryllium molecule, there are 2 electrons each. The first 2 electrons enter into the sigma 2s and the next 2 electrons enter into the sigma star 2s. So, bond order will be calculated as 2 plus 2 4 minus 2 plus 2 4. So, 4 minus 4 divided by 2, which comes out to be 0. Again, since the bond order is 0, which means that the beryllium molecule will not show its existence. So, beryllium molecule does not exist. Next, coming to nitrogen molecule. Now, the nitrogen molecule or the electronic configuration of nitrogen is 1s2, 2s2, 2p3. So, here in this diagram I have shown the 2s orbital and 2p orbital. 1s is the KK shell, so it is completely filled. This is the energy depicting the orbital's energy. Now, in this case, the 2s orbital of nitrogen has 2 electrons each, out of which 2 enter into the sigma 2s, which is the molecular orbital, and 2 enter into the sigma star 2s, which is the anti-bonding molecular orbital. In case of nitrogen, the 2p3, so they are same energy orbitals, so each 2p will have, atomic orbitals will have one single electron. So, they are singly occupied, and in this case, first 2 electrons will enter into pi 2px and pi 2py respectively, one in pi 2px, one in pi 2py. The next 2 electrons will again enter into first pi 2px and then pi 2py, because pi 2px and pi 2py, they are of same energy. So, they are going to be singly occupied first and only then the pairing will take place. And the 2 electrons which are left, they are going to be filled into sigma 2pz. If we calculate the bond order, then in this case the bond order will be calculated. Bonding molecular orbital have 2, 4, 6, 8. Total number of 8 electrons in the bonding molecular orbital and 2 electrons in the anti-bonding molecular orbital. 1s electrons, they are going to cancel out each other. So, 8 minus 2 divided by 2, which comes out to be 3. So, which shows that the 2 nitrogen atoms, they are bonded together by 3 bonds. And since the outermost orbital of nitrogen has paired electrons, therefore, the magnetic behavior of nitrogen will be diamagnetic. The molecule is diamagnetic in nature. Coming next to the oxygen atom. In this case of oxygen atom, again electronic configuration of oxygen is 1s2, 2s2, 2p4. So, again in this diagram I am showing only the 2s and 2p orbital. The 2s orbital is atomic orbitals, they are completely filled. So, 2 electrons get filled into the sigma 2s and the next 2 get filled into the sigma star 2s. And the 2p orbital of oxygen has 4 electrons each. So, first 2 electrons will enter into sigma 2pz, then pi 2px and pi 2py, they are going to be singly occupied by the electron, then pairing will take place, and finally the 2 electrons which are left, they are going to be filled into the pi star 2px and pi star 2py orbital. Now, here the bond order comes out to be 2, which shows that the two oxygen molecules, they are joined together by the two bonds. And since the outermost orbital, which is the pi star 2px and pi star 2py, they are singly occupied because they are of same energy, and pairing will not take place till the same energy orbitals are singly filled. Since they contain unpaired electrons, therefore the magnetic behavior of oxygen is paramagnetic in nature. So, oxygen molecule is paramagnetic in nature. Coming to the combinations for p orbitals. Now, in case of p orbitals, two types of bonding can take place: head-on bonding, which means the formation of sigma bond, and lateral overlapping, that is the formation of the pi bond. So, in this diagram, there it is, the lateral overlapping is being shown. How pi 2px is being formed? Pi 2px is being formed by the additive combination of the 2px orbitals. When the same sign get combined, then it results in the formation of additive combination and pi 2px orbital will be formed. But if the wave sign or the sign is different, it will result in the formation of pi star 2px and a node will be formed in between. Similarly, in the case of sigma bonding, the head-on bonding with the same sign, if same sign orbitals are combining, if this is positive, then this will also be positive. So, when both the positive they combine, it leads to the formation of sigma 2pz, and sigma star orbital is formed. If one is positive, the another one will be negative. So, negative, positive, negative, positive. If positive and negative in the center, which results in the formation of a node. So, increasing number of nodes are there. In this case, there is combination, then one node, then there are two nodes and finally there are three nodes in the sigma star 2pz. So, this is positive, this is negative, again this is negative, this is positive. So, positive negative node, positive negative node, negative positive node. So, there are going to be number of nodes will increase. So, this is the how pi and sigma bonds are formed in the case of p orbitals. This is a diagram showing how sigma, pi, pi star and sigma star, they are related to each other in terms of energy. So, sigma 2p energy is least, then pi 2p, then pi star 2p and finally the sigma star 2p. Now, coming to the sp orbital overlapping. Now, the filling of molecular orbital, it takes place in two ways. First, filling is up to from up to nitrogen molecule, that is up to 14 electrons, and that filling is sigma 1s, sigma star 1s will be there, but sigma 2s, sigma star 2s, then pi 2p and then sigma 2p. Pi 2p is lower in energy in comparison to the sigma 2p up to 14 electrons, because when the number of electrons is less, there is less effective nuclear charge and there are interaction between the orbitals of the same type. That means there are interaction between sigma 2s and sigma 2p and sigma star 2s and sigma star 2p. So, these are the interactions which are going to take place, which leads to the stabilization of, this will lead to the stabilization of sigma 2s and destabilization of sigma 2p, because the energy difference between sigma 2s and sigma 2p will increase. There are interactions between sigma 2s and sigma 2p, and these interactions, they are repulsive in nature. So, when there are repulsion between sigma 2s and sigma 2p, they are going to move away from each other. So on movement from away from each other, sigma 2s will move towards lower side and sigma 2p will move towards the higher energy side. As a result, the pi 2p becomes lower in energy. But on greater than 14 electron, that is after nitrogen, if we come to oxygen, then the sigma 2p, since the number of electrons have increased, so this interaction becomes less and less. There is difference between the orbitals. As a result, this sigma 2p again takes its original position and it comes in lower in energy. So this is sigma 2p because head-on overlapping or the sigma bond results in a strong bond and its energy is lower in comparison to pi 2p. So two types of filling are there. One is up to nitrogen molecule, which shows that the electrons are filled as sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px, pi 2py, which are of same energy, and then sigma 2pz. But it changes from oxygen. It shows that it is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then sigma 2p, then pi 2px, pi 2py, and then pi star orbitals are there. This I have shown diagrammatically, relative energy levels for 2s and 2p. Without big 2s and 2p repulsions, when there are no repulsions or less repulsions, in that case sigma 2p, which is a stable bond, it is of lower energy, and pi 2p is of higher energy. But if there are big repulsions between 2s and 2p, as a result of this repulsions between sigma 2s and sigma 2p, sigma star 2s and sigma star 2p, they become lower in energy, and these sigma 2p and sigma star 2p, they become higher in energy. When sigma 2p becomes higher in energy, then pi 2p energy becomes lower in comparison to the sigma 2p. So pi 2p gets filled first. So this is the case with big repulsions. Thank you.